Hello, we're here today to cover the third multiplication for vectors, and that is the cross product. And before we can do that, we have to cover a topic that allows us to perform this third multiplication. So what we have to talk about is the determinant, what it is, and how we calculate it. And it's hard to give it a name as to like what it is because typically a determinant is used in applications, and so determinants are used to do many things. In mathematics, it's just a determinant and it calculates something, but it always calculates that thing in the same way. So we're going to focus on like how to do that, and then we'll apply that to the cross product and talk about what that's giving us. Okay, so with the determinants, we have a few different types of notation, and in particular, we have what looks like absolute value bars on a capital A actually just means determinant of A. And so you see the two different ways to write that. It's like those magnitude bars with an A or det of A. Either one is acceptable, but you just need to know when you see one or the other that it means the same thing. Now, in order to calculate a determinant, we have to be working with a square matrix, which means it's either 2 by 2, 3 by 3, 4 by 4, and so on and so forth. In this class, we'll only ever really deal with determinants of a 3 by 3 and no more than that. So for a 2 by 2 determinant, what we would have is a matrix that has 4 components in it, 2 rows, 2 columns, and we would start at the upper left corner of the matrix value, and we would go down in a diagonal manner and find a product, A times D. Then we would come to the lower left corner. We would subtract the product of C with, now follow a diagonal to B. Okay, so it's always going to be like that sort of, cross product sort of thing going on there when we're calculating a 2 by 2 determinant. For a 3 by 3, the same notation is used. Like we can still use det of A or those magnitude bars with A. But there are two different ways that we can do the calculation. The first one is kind of weird. So in this particular picture here, what I have here is a 3 by 3 matrix that is inside these black brackets. And so we've got A1, A2, A3, B1, B2, B3, C1, C2, C3 for the 3 columns of our matrix. Then outside of the matrix and to the right of it, we list the first 2 columns over again. And then we start at the upper left corner of our array of numbers, and we go down in a diagonal and we find a product. So that first diagonal would be A1 times B2 times C3, and we see that right here down below. Then we move over to the right by 1. We get to B1, and we find another diagonal product that will be plus B1 times C2 times A3. There's that second product. Then we move over, we go to the third column and go down in a diagonal from C1 to A2 to B3, and that's our third product. Then what we do is, and I think different schools of thought do this different, I typically come down to the bottom left corner and I think minus, and then I put some parentheses around what I'm going to do next, okay? So I start at the bottom left corner, and I go up in a diagonal and I get a product, A3 times B2 times C1. That's this first product. Then I move on, I go to B3, move over to one to the right, and I get another diagonal product, B3 times C2 times A1. There's that product. And then finally start at C3 and go in my diagonal. I have C3 times A2 times B1. There's my third product. Now that all has to be in parentheses because we have to subtract all of it. Now that's one way to calculate a 3 by 3 determinant. Another way is where this is actually the definition of the determinant down here. What I just got done showing you is kind of the result of what we're going to do now. It's like the shortcut to get what you want. But in reality, the way to calculate a determinant is you start with Now, first of all, I'm going to say that we could do this about any row or any column. But what I do is above my first row, I write my signs, plus, minus, plus. And then I take the first component in the first row, first column, and I imagine crossing out the row and the column that it's in. So that's like this representation right here, okay? So I circle A11, I cross out the column that it's in, I cross out the row that it's in, and that leaves behind this A22, A23, A32, and A33, and I still have to find a 2 by 2 determinant of that. And then once I find that determinant, that's right here, I'm going to multiply that number by the A11. Then I move over to A12. I meant to change colors there. So the A12, I'm going to circle it. Notice there's a minus sign above it. That means I need to put minus A12. And so I have that. So see the minus sign there? Got it in. And then up above it is where we circle A12, we cross out the column that it's in, we cross out the row that it's in, and we're left with 4 numbers. And those 4 numbers need to plop down into a determinant that we are going to calculate. Last but not least, we move over to the third column where there's A13. There's a plus sign over it, so we're going to add A13, and we see that right here. And then up above, we can see where we circle A13, cross out the row it's in and the column it's in, and then we're left with 4 numbers that go into a determinant, and we'll have to calculate a 2 by 2 determinant. And so then to finish this off, we would just, let me come down here and say this is equal to A11 times A22, A33 minus A32, A23 minus A12 times, and then I have to do that again, that same diagonal product thing. So I get A21, A33 minus A31, A23. And then I get to my third piece, and that's going to be plus A13 times, and again, I do that diagonal product. So it's A21, A32 minus A31, A22. Now, of course, these are going to be numbers in any calculation that you make, so you don't have to worry about all those sub numbers in there. But that's kind of the gist of how we calculate that. Now let's calculate some determinants. We're going to do a simple 2 by 2, and then we'll do the 3 by 3 both ways. Okay. So here I'm finding a determinant for a matrix A, where A has components 1, -2, 3, and -4. When I read off components of a matrix, I always start at the top left, and I read off my rows. So I do row 1, then row 2, then row 3. Okay. So the determinant of A, we'd write det of A, or we would write the A in those bars. And then we would write the matrix itself in those straight up and down bars and put the components in. All right, we need our diagonal product. And so that's going to give us 1 times -4 minus 3 times -2, which gives me -4 plus 6 for a total of 2. Okay, not too bad. Now let's try the determinant of a 3 by 3. So this is B, determinant of B. I'm going to do the trick way or the shortcut way first. So we have 1, 2, 0, -2, 3, 1, 4, 0, -1. And then I need to relist the first 2 columns. So it's 1, -2, 4, 2, 3, 0. Okay. I have my 3 products, 3 diagonal products that need to occur starting from the top left. Those will be 1 times 3 times -1 plus 2 times 1 times 4 plus, ooh, looks like that third one gives me a 0. Take full advantage of that. Now I have minus all the next three products. So I'm starting at the bottom left and doing a diagonal product and then moving over and then moving over. So I get 4 times 3 times 0, oh that's going away, plus, there's another 0, plus a -1 times -2 times 2. All right, so we just have to simplify this. This gives me a -3 plus 8, and then I have minus 4. So in total, this is going to give me 1. That's nice. All right, let's do it the other way. So the other way better give us the same answer. So we're looking at the determinant of 1, 2, 0, -2, 3, 1, 4, 0, -1. We start with the upper left corner. We have 1 there. Imagine the row and column it is in being gone. You're left with a 2 by 2 determinant for 3, 1, 0, -1. Then we move over to the second column, and remember that's going to be a minus sign. So we have -2 times the determinant with, and now imagine again, the row and column it's in are gone. So the components left are -2, 1, 4, -1. And then finally, we have 0, and that's plus. And that's all I'm going to write, because 0 times anything is 0, and that's a great thing. I don't have to calculate anything there. Now going back to my calculations, this is equal to 1 times -3 minus 0, minus 2 times, my diagonal product will give me 2 minus 4, and that's it. Finishing this out, this is -3 minus 2 times a -2, and that all multiplies and adds together to give me a 1. Awesome. All right, so those are the two different ways, and that's just the determinant. We're not going to use the determinant solely in this way. We're going to use it to calculate a cross product. So now we can talk about the cross product. Right here I've got a picture of two vectors, u and v, and so the way to determine geometrically what we're calculating when we do a cross product is to lay the palm of your hand or the side of your hand on the first vector. So if we're finding u cross v, I would put my hand on the u vector and curl my fingers towards the v vector, because that's the direction I want to cross in. My thumb I will leave up and it will be pointing straight up. That result, the u cross v, is my thumb. It's the vector that points perpendicular to both u and v. And so that's kind of the golden rule. Fortunately, I have a nice picture here. This is showing the right-hand rule for determining the direction of the result of a cross product. All right, so that's geometrically. Now, algebraically, the way that we calculate this is a cross product, which is a determinant, which is what we just did. However, there are two things here. One of them is the first row in your determinant is I, J, K. Those are our standard basis vectors. Remember, each of them only has one non-zero component, and it's a 1. So these are unit vectors. And then the second row will be the first vector in the cross product. The third row will be the second vector in the cross product. And then we go through the same process. Like they've kind of shown us right here. You take the I hat and you're going to plop it down, and then you're going to multiply by, after you imagine the row and the column being gone, you're going to multiply by the determinant of the remaining two columns and 2 rows. And then you move over to J hat, do the same thing, and then K hat. And we have a plus, minus, plus for our signs. Now, I did steal this image from online, and so I can't take ownership for this, but I can correct it. They accidentally switched their negative sign to a positive sign, and it should be a negative sign. Okay, so don't do what the image did. Make sure that's a negative sign. Okay, now what ends up happening is that we end up with a determinant value on those 2 by 2s, and that's going to be a number. So you'll have a number times I hat, a number times J hat, and a number times K hat, which is just a vector. So let's see how we can do this. In this next problem, I'm asking you to calculate A cross B and B cross A. So I'm going to set everything up. I have my I hat, my J hat, my K hat. I have 4, 3, -2, 2, -1, 1. And I'm going to do it the way that I'm most comfortable with, and you can do it whichever way you would like. I showed you 2 different ways. I'm not grading you on them. You choose the one that works best for you. So I start with my I hat. So I'm going to get I hat times the 2 by 2 matrix or determinant with 3, -2, -1, 1. Then I do minus J hat, and it's going to have 4, -2, 2, 1 for the determinant. And then I go to positive K hat multiplied by the determinant with 4, 3, 2, -1 in the components. Okay, so this is going to give me an I hat times 3 minus 2 minus J hat times 4 minus a negative will be plus 4 plus K hat, and then here we're going to have minus 4 minus 6. Okay, simplifying this just a little bit, we get I hat minus 8 J hat minus 10 K hat. This is the standard basis form that we learned last time for vectors. And of course, the equivalent form would be to drop the I, J, K and use angle brackets and use the constants that are in front of I, J, and K. So we'd have 1, -8, and -10 for our vector. Okay. Now let's look at B cross A. Now the idea here is that, I talked about this in class. The idea here is that we're going to see some sort of relationship between A cross B and B cross A. And in particular, we will see that one is the negative of the other. And we demonstrated this in class with the idea that if you're curling your hands from U to V, but now you want to find V cross U, you have to turn your hand over to curl from V to U, and now your thumb would be pointing straight down, which is negative of the original U cross V. Okay, so I'm going to do B cross A, and I'll show all the steps. We have I, J, K, 2, -1, 1, 4, 3, -2. This is going to give me I hat times the vector or the determinant with -1, 1, 3, -2, minus J hat, and a determinant with components 2, 1, 4, -2, plus K hat, and that's got 2, -1, 4, 3. Okay, now I'll do my diagonal products. We have I hat times 2 minus 3 minus J hat times -4 minus 4 plus K hat times 6, and that is a negative sign up there. Yep, so this will be 6 minus a -4, so it'll be plus 4. That simplifies to be negative I hat plus 8 J hat plus 10 K hat. Or we could also write that in the equivalent angle bracket notation with -1, 8, and 10 as components. And notice that that is actually exactly negative of A cross B. And that kind of leads us directly into the first property of the cross product. Now, I like to talk about the second property first, because the second property tells you that if you have a constant that's multiplied by one of the vectors and you're going to do a cross product, then that constant can go with either the first vector or the second vector or outside in front and wait for the cross product to happen. But it does not go to both of them. And so in particular, in number 1, where if A cross B is equal to -B cross A, what that actually is, or an alternative way to write that, is that it's equal to a negative parentheses B cross A. Okay, so that negative sign can be with a B. It could be with the A as well. So it could be B cross a negative A. That would be the same thing as well. But somewhere or another, that negative's got to show up in order for there to be equality there. So the number 2 property where C can be, it can associate with one of the vectors, the other vector, or the full cross product. That is the associative property. And then in 3, we have A cross a sum. This is how we would distribute a cross product to a sum of vectors. So this is the distributive property. And that's distributive on the left. Number 4 is how do you distribute on the right, but it's still just a distributive property. In 5, the only name I have for this is the scalar triple product. And then in 6, we're dealing with cross products, and we're showing an equivalent statement that is dealing with dot products. It's kind of weird. But so maybe we could call this the conversion between 2 cross products to dot products. I mean, that's about as simple as I can write this. It's just weird. Okay. I've never used 6 before. It's not something that's intuitive. It's not something that I remember. It's not something I've ever needed, but it is a property, so it's listed. All right, moving on. In these following examples, the idea here is to look at the expression and determine if it is something that is possible to do. If it's possible to do, then it's meaningful, and we're supposed to state whether we would get a scalar or a vector answer. So I'm looking at A, and I have A dot and then B cross C. Now going inside to the parentheses, B cross C is a vector, right? And A is a vector. So this is the equivalent of looking at a vector dotted with a vector. And you can dot product 2 vectors. That's actually the definition. You need 2 vectors to dot product. The result would be a scalar. So that's meaningful. We're able to get a value. The second one, B, now the parentheses are around a dot product and the cross product is outside. If we calculate a dot product, we will get a scalar. So what this is saying is take a vector and cross it with a scalar. We just got done doing the cross products. They require vectors. This is nonsense. There is no meaning to this. It cannot be done. The next one is A cross, and now our parentheses are around another cross product. The cross product in the parentheses would give us a vector. So we have a vector crossed with a vector. And that's totally doable. And by definition, we need 2 vectors to get a cross product. The result of 2 vectors being in a cross product is a vector. A dot, and now again we have our parentheses around B dot C. Well, B dot C is a scalar, and so this is saying take a vector and dot it with a scalar. But we can't do that. In order to do a dot product, you need 2 vectors, and so this is nonsense. No meaning, can't do anything with it. Okay? You'll have a homework problem that goes through several of these, and so this is just kind of to alert you to it and like what you're supposed to do. Okay, applications of the cross product. And this is where we kind of left off in class, and I'm sorry to leave you hanging on there, but I'd like to take the time to go through this in the video so that we can kind of slow it down just a little bit, and it gives you the opportunity to kind of try the problem on your own like I would have you do in class, but also be able to have that guidance as you need it working through any problem. So we have another way to calculate angles between vectors. I do want you to recall from 12.3 that we were told a dot product of 2 vectors is equal to the magnitude of A, the magnitude of B, times cosine of the angle between them. And that allowed us to solve for theta by doing some division and taking a cosine inverse. We got that theta is equal to the cosine inverse of A dot B over the magnitude of A times the magnitude of B. And so these are, this is different from what we're seeing right here with the sine of theta, but notice it's two different ways to find an angle between two vectors. Now, when, and in the recall, when A dot B equals 0, we found out that theta was equal to pi halves, and A and B are perpendicular because the angle between them is pi halves. For this next one, when we're doing the angles between vectors and we're dealing with cross products, what we have is the magnitude of our cross product of A and B is equal to the magnitude of A times the magnitude of B times sine of our angle. And then we can isolate the angle and we can get this next expression that theta is the sine inverse of the magnitude of the cross product divided by the product of the two magnitudes of A and B. That's a lot, and that's actually quite a bit to calculate to find that. And every now and then that's the one you're going to have to use. Admittedly, the dot product definition for finding the angle between two vectors is easier. It definitely is, because you don't have to do a cross product. Dot products are easier. However, what we get out of this is that if A cross B is equal to the 0 vector, then the magnitude of A cross B is equal to 0. And theta, which would then be sine inverse of 0, would be equal to 0 or 180 degrees. And what that means is that A and B are parallel. So now we have two properties that are coming out of the dot product and the cross product. One is that if the dot product is 0, the vectors are perpendicular. Let me see if I can summarize that here. So 1, let me just write it out. If A dot B equals 0, the vectors are perpendicular. And 2, if A cross B is the 0 vector, the vectors are parallel. So now we have a test. Like if we're just dealing with two random vectors and we're asked, hey, are these parallel or are these perpendicular? Those are our two tests. Find the dot product. If it's non-zero, the only thing you can conclude is that they're not perpendicular. So then you find the cross product. If the cross product is 0, now you know that they're parallel. If the cross product is not 0, now you know that they're not parallel, right? So we can tell like what sort of relationship they have. All right. Now with the cross product, we are able to find a few different things. Number one is we are able to find the area of a parallelogram. Now a parallelogram is two triangles. That's all it is, if you think about how it gets put together. So we have a parallelogram drawn here. If I was to connect, actually that's, yeah. If I was to connect that, then you see we have two triangles right there. And the area of a triangle is 1/2 base times height. So because a parallelogram is two of the same triangle, then the area should just be twice the area of a triangle, which means that we need to be able to find a base and find a height for a parallelogram. Now, there's always going to be an angle between the two vectors that are put together to form a parallelogram. And so that angle will allow us to go further with this, okay? Now, if I want to find the height of this parallelogram, let me just delete these guys right here. When I want to find the height of a parallelogram, I'm looking for this right here. And we know that in order to find this value right here, well, we would need to be able to remember that, like, let's just call this question mark for now. Sine of theta is equal to the opposite, so that's going to be the question mark, over the hypotenuse. Our hypotenuse is over here. It's the magnitude of the A vector. That's the length of the A vector. Okay, so then we can solve for the question mark. Question mark is going to be the magnitude of the A vector times sine of the angle. That's going to give us the height of our parallelogram. And then the base is just going to be the magnitude of the B vector, since the B vector is forming the base of the parallelogram. And so that's how we get that the area is equal to base times height. And the way this is written is this is actually the height, and then this is the base. And we can reorganize these to be the magnitude of A times the magnitude of B times sine of the angle in between A and B. But from before, what we learned is that this product of the two magnitudes times the sine of the angle is just the magnitude of the cross product. So that means we don't even need to know the angle between two vectors that form a parallelogram. We just need to know the vectors. Then we can calculate their cross product, and then we can find the magnitude of the cross product. So we're going to do that. We are given vertices of a parallelogram. When you are creating a parallelogram and you're told 4 vertices, go in order around. So I'm just going to draw myself a random parallelogram in space. I cannot possibly draw this accurately in 3D, so I'm not going to even try. I'm just going to draw it in space like this. And then I'm going to go around and label A, B, C, D. Okay. Based on my drawing up above, the image that's up above, I need to form 2 vectors that start at the same place. So those vectors are going to start at A. One of them will be the directed line segment AB. The other one will be the directed line segment AD. I will call these A and D. Okay? But I have to form those. All right, so first, A is equal to the directed line segment AB. In order to form AB, I'm going to make my angle brackets. I need to take the components of my B point and subtract the components of my A point. So in the first component, that's 3 minus 2. In the second component, that's 3 minus 1. In the third component, that's 1 minus 0. And that simplifies down to 1, 2, 1. My D vector is going to be the directed line segment AD, which I need to form as a position vector. So I'm looking at A and D now, and I do the same thing. I take the first component of D, which is 4, subtract the first component of A, which is 2, go to the second component, I have 1 minus 1, and then third component is 0 minus 0. My final position vector has components 2, 0, 0. Okay. So then, to recall, the area is going to be the magnitude of A cross D, since I named my vectors a little bit differently. So I need to find the cross product of A and D. So I line them up. A cross D is equal to, and I'm going to set up my determinant, ijk. I have A, which is 1, 2, 1, and I have D, which is 2, 0, 0. And so I'm going to have I hat times the determinant with the components 2, 1, 0, 0, minus J hat Imagine the row and column gone. This leaves behind 1, 1, 2, 0, plus k hat, and that's going to leave us 1, 2, 2, 0. These zeros are going to come in handy. So I calculate this. I have my I hat times 0 minus 0. That means I have no I hat. Minus j, and I get 0 minus 2, plus k hat, and I get 0 minus 4. So this simplifies down to a vector with components 0, positive 2, negative 4. Okay, I'm almost there. I just need to get the magnitude. So the area is equal to the magnitude of this vector I just found, not A cross B, but A cross D. So it's the square root of 0 squared plus 2 squared plus negative 4 squared, which gives me the square root of 4 plus 16, or root 20. We could also write this as 2 square root of 5, but either way, 1 is totally correct. Okay, so that's the area of the parallelogram that would be formed with these vertices. The next application is to be able to find the volume of a parallelepiped. I never know if I'm saying that right, if it's parallelepiped or parallelepiped. I learned it as parallelepiped. My Calculus 3 instructor was from Iran, and that's the way he said it, and that's how I learned it. So I may be saying it wrong. But a parallelepiped is just like a box that is being slanted. That's it, okay? And we may want to calculate the volume for this rectangular box. And we know that the volume for a regular rectangular box that hasn't been slanted would just be length times width times height. Or you could also think of it as the area of the base times the height, okay? Well, we know what the area of the base is, right? We just got done calculating the area of a parallelogram. So the area of the base is equal to the area of the parallelogram. Okay, and so in our case, that's going to be the magnitude of B cross C. Okay, so I've got that written out here where we've got the base figured out, but we're still trying to deal with the height. Now the height can be found doing a little bit of geometry and trigonometry. The height can be found to be the magnitude of A times cosine of the angle, okay? And that's in this little picture right here, right? Using the similar tactic to what I did up here to figure out how do we get that unknown height, okay? All right, so once I have that the height is the magnitude of A times cosine of the angle, I can kind of put those things together and say, all right, we've got the magnitude of A times the magnitude of B cross C times cosine of the angle. And they're telling us that this is the same as finding A dotted with B cross C and then taking the magnitude of that. And where this is coming from is directly from the definition of the dot product. Totally is. Look at this. One of my vectors is A. I've got the magnitude of A. My other vector, even though it's ugly, is just B cross C. But the result of it is a vector in there. So I have a magnitude of a vector times a magnitude of a vector times cosine of an angle. That should be equivalent to the dot product of the two vectors. Now, we're dealing with volumes, and that's why we have these magnitude bars on there. Those are actually absolute value bars for once, because cosine of the angle could give us a negative value, and so we have to be careful of that. So if you get a negative value, just know that you got to make it positive, because it's volume, it's a physical dimension. This product right here, A dotted with B cross C, is called the scalar triple product. And we saw this up in the properties of cross products, and that's where I named it the scalar triple product. All right, we are going to find the volume of the parallelepiped determined by the three vectors given, A, 1, 3, negative 1, B, negative 2, 1, 3, and C, negative 1, 3, 1. Okay, so this is telling me that I should, in theory, be able to just say B is equal to the in absolute value or magnitude, A dotted with B cross C. Okay, so we need to calculate a few things first, right? We need to figure out what is A dotted with B cross C. Now I'm going to show you something because I want you to see it, and it's one of those things that if I just tell you, it makes zero sense, but if I do it, it'll make more sense. A dotted with B cross C can be calculated super fast compared to what you may be thinking. We can calculate it by finding the determinant of a 3 by 3, where the first row has A in it. Okay, so we're going to have A, B, and then C. Okay, so I'll go ahead and put those in there. The A vector has 1, 3, negative 1. The B vector has negative 2, 1, 3. The C vector has negative 1, 3, 1. Now, why does this work? And why would she show us this when she hasn't explained or shown it the other way? Because when we are dealing with the cross product and we have the I, J, and the K in that top row, and then we have A and B in the second and third rows, let's just go back to one of those calculations right here. When you have I times the determinant of a 2 by 2, you're actually taking the first component of a vector times the first component of another vector. And so the math works out. I'll show you and do this both ways, but I want you to have a faster way to calculate this. Okay, so I'm going to calculate this determinant, starting with 1 where it's positive. I get 1 times the determinant with 1, 3, 3, 1. Then we go to the 3. We have minus 3 times the determinant with negative 2, 3, negative 1, 1. Then we move to the negative 1 where it's positive. So it'll be plus a negative 1 times the determinant with negative 2, 1, negative 1, 3. All right. And this gives us 1 times 1 minus 9 minus 3 times negative 2 minus a negative, so plus 3, minus 1 times negative 6 minus a negative will be positive 1. And that all adds up to, let's see, that'll be a negative 8 minus 3 times 1, which will just be minus 3, minus 1 times the negative 5. All right, looks like I have negative 11 plus 5, which is negative 6. So V is equal to the absolute value of negative 6, which is positive 6. Now, doing it the other way around, I'd have to calculate B cross C first. Like this. So I'd have my I, J, K, and then I'd have my B vector, negative 2, 1, 3, negative 1, 3, 1. This would be I hat times 1, 3, 3, 1 minus J hat times negative 2, 3, negative 1, 1 plus K hat times negative 2, 1, negative 1, 3. Notice the parallel to what I have up here. Like in place of I, J, and K, I have 1, 3, and negative 1. Those are the components of A. Down here I have the components of I, J, and K. So it's so far working out to be what I said it was. This is going to multiply out to give me, looks like 1 minus 9 is negative 8 I hat. And then negative 2 plus 3 is 1, so I'll just have minus j hat. And then I get negative 6 plus 1 is negative 5 k hat. Okay, now I'm supposed to look at A dotted with B cross C. A is 1, 3, negative 1, dotted with B cross C. Well, that has negative 8, negative 1, negative 5. And that gives me, multiply the like components together, then add. So we'll get negative 8 minus 3 plus 5 is equal to a negative 6. And then the volume is going to be the absolute value of negative 6, which is 6. So you choose the way you want to do it. I just wanted you to see one shortcut because we have to calculate an awful lot in this class. It's nice to see where things can go faster. All right, next application is torque. So if we have a force and it's acting upon a rigid body, that just means a body that's not moving, right? It's not going anywhere. And it's acting on a rigid body at a point that is given by a position vector r hat. Then the torque, that's a tau hat, that's relative to the origin, is going to equal the cross product of the position and force vectors, and it will measure the tendency of the body to rotate about the origin. Sorry, let me just take a quick pause to get a drink of water. Okay, so sorry about the pause. We're dealing with torque, and we're told that we should just be able to find the cross product of the position vector with the force vector, and that will tell us the torque. And that is this iteration of torque. So if we knew the position vector, we knew the force vector, then we could easily calculate these. But if we know the angle between a position and force vector, and we don't actually know the force vector, or maybe we don't even know the position vector, but we just know the magnitudes, then we can use this next value in order to make our calculations. Okay, so then the magnitude of our torque would be the magnitude of the position vector r times the magnitude of the force vector F times sine of the angle between them. So we've got this particular situation. We've got a wrench. It's a 30 centimeter long wrench. Right away, centimeters we know are not proper units. We need to convert those to meters, so we'll do that. So 30 centimeters long wrench lies along the positive y-axis. That's going to give us a vector right there, okay? It's gripping a bolt at the origin, and then a force is applied in the direction 0, 3, negative 4 at the end of the wrench. We want to find the magnitude of the force that's needed to supply 100 Newton meters of torque to the bolt. So there's a whole lot packed into here. Number one, we're given that the position vector r is lying along the positive y-axis, and if it's lying across the y-axis, that means that the x-axis is, or the x-coordinate is 0. The y-coordinate or component is, I'm going to go ahead and convert, 0.3, and that's 0.3 meters, and the z-component is 0. The magnitude of r is going to equal just the 0.3, since we only have one non-zero direction here. Okay, that's not a whole lot that we just got. Now the force, this is the tricky part of the question. The force is applied in the direction of 0, 3, negative 4. That doesn't tell us what our force is. So this sentence right here, all that is telling us is that our force is applied in that direction. So F, our force, is applied, get my writing better, in the direction of of 0, 3, negative 4. So we have to somehow use that to help us out here. And so what we're going to do is we're going to use a little bit of trickery here. It turns out that if we wanted to, we could make this direction into a unit vector. And so then what we could say is that our force, with all of its magnitude divided out, like all of it, so it's a unit vector, is equal to this direction vector, 0, 3, negative 4, with all of its magnitude divided out. Okay, so we could look at this ratio, and then that can give us the information that we need. So that means this is equal to the square root of 25, that's 1/5, and then our vector 0, 3, negative 4. Okay, so I can use this equality to say that my vector is equal to the magnitude of my vector, f, over 5, times the vector 0, 3, negative 4. So now I have my f vector built. And it is written in terms of my magnitude vector, but I can still use that in order to get what I need. Let's see, what can we do? We need, let's see, the magnitude of F if it's known that the magnitude of the torque, tau, is equal to 100 Newton meters. So we're going to use the fact the magnitude of torque is equal to the magnitude of the cross product of R and F. Okay? So that means we need to calculate a cross product of these two vectors that are here. And hang on 1 minute, because it looks like I might not be recording. I'm not sure. I think I am recording. I'm going to keep going with it. I don't see my record button. Okay, so what I need to do is I need to find R cross F. We have R up here. We have F down here. It's not the nicest looking F, but it'll do. And we're going to find R cross F. And those two vectors are 0, 0.3, and 0. That's my R, crossed with the magnitude of F over 5 times the vector 0, 3, negative 4. Now we learned some properties about scalar multipliers being in here, and they say that we should be able to pull that scalar multiplier out to the front and then go ahead and deal with our cross product inside so that we're not carrying around too much in our vectors. Just makes things a little bit cleaner. So then I need to figure out what this cross product is. And in order to do that, I've got to just set up a cross product. So kind of off to the side here, I've got I hat, j hat, k hat. I have 0, 0.30, and I have 0, 3, negative 4. A whole lot of things are going to go to 0. This is equal to I hat times the determinant was 0.303, negative 4, minus j hat. J hat has 0, 0, 0, negative 4, plus k hat, which has a determinant with 0, 0.3, 0, and 3. That one's also going to 0. So I end up with a negative 1.2 j hat, or this can also be, sorry, that's not a j hat, that should be an I hat. So this can also be written as negative 1.2, 0, 0. That is my cross product. So I'm going to go back in here and say that I've got the magnitude of F over 5 times negative 1.2, 0, 0. That's the result of my cross product. Now if I take the magnitude of this, the magnitude of R cross F, is just going to be the magnitude of, well, it's a little weird to write, but let's do it this way. We have the square root of the magnitude of f squared over 5 squared times 1.2 all squared. And there's a plus 0, but we don't need to deal with that. So everything just ends up getting squared, and we end up with 1.2 times the magnitude of f over 5. Okay, but the magnitude of tau is equal to the magnitude of r cross f. And we know that the magnitude of tau is 100. So what we have here is the magnitude of tau is equal to 1.2 times the magnitude of f over 5 is equal to 100, which means the magnitude of f is equal to 500 over 1.2, which works out to be 417 Newton meters. And that's it for that one. I think I need to stop this video and